we're going to be discussing how we can improve quantum attacks on block ciphers, paying special attention to the case of the Advanced Encryption Standard. This is joint work with James Davenport at the University of Bath, and my name is Benjamin Pring, and I'm from the University of South Florida. So the big question we want to ask is, do we really need so many quantum resources to attack block ciphers by quantum search techniques? And the answer we arrive at is no, which is a good thing or a bad thing depending on who you are. So Table 1 summarizes our results with respect to the Advanced Encryption Standard. We have the last best attack on the left and our improvements on the right. We have the number of quantum gates or logical operations we need to perform, the circuit depth or amount of time we need, and the number of qubits or amount of quantum hardware we require. And starting from the amount of hardware, we can see that we get a reduction of a half to a third. The time required remains roughly static, and the number of quantum gates drops again by a factor of a half to just over a third. So the big takeaway is we can do more with less. So let's review what block ciphers are. We have an encryption function and a decryption function, and each of these take in a key of length k bits, and they work on message blocks of length n bits. And we have this relationship here, which essentially means we can decrypt anything we can encrypt under the same key. So block ciphers have the property that we fix a key and vary the plaintext, and we have a pseudo-random permutation, but we'll be looking at the case where we actually want to fix the plaintext p and vary the key k, in which case it behaves as a pseudo-random function. So looking at AES in particular, we have k is either 128 bits, 192 bits, or 256 bits, and the message block is always going to be of size 128 bits. We're going to be looking at attacks in the noise-free model of quantum computation, as Grover's algorithm in that model is currently the leading technique, and we're looking for two reasons. One is that the NIST security levels with post-quantum standardization competition are currently based on the concrete cost of breaking AES, and two, it's an interesting case study in how we can optimize quantum circuits and algorithms. So let's consider the attack scenario. We're given R unknown plaintext ciphertext pairs for a fixed and unknown key k star. So these are simply pairs of message blocks, one of which is a plaintext and one of which is a ciphertext, and we're guaranteed that for any index we have this relationship here, i.e. the ciphertext is an encryption of the plaintext under this key k star. And we're also given the classical circuits for encryption and decryption. And the goal is to recover this unknown key k star. So this can be formulated as a search problem by constructing a function chi, which accepts the key and outputs 0 if it isn't the search target, i.e. the key we're looking for, and 1 if it is the key we're looking for. And explicitly we can construct chi by creating a function where we input a candidate key, k, and then we perform R separate tests. And each test consists of taking a plaintext, encrypting it under the key, and checking does it match this corresponding ciphertext. So a natural question is, how large does R have to be, and what impact does this have on the cost of the computation? Well, for correctness, we want that the function chi only has one key, k star, that evaluates to 1. So we're guaranteed that this exists by the scenario, but we also have the other 2 to the k minus 1 other keys to consider. So if we take any other key that isn't the key we're looking for and encrypt a plaintext under that key, then compare just one bit of that encrypted plaintext with a corresponding bit of the ciphertext, then it'll have a probability of half that it matches. This is just a standard property of it being a pseudo-random function. So the expected number of matching keys, or the expected number of solutions to chi which evaluate to 1 is 1, i.e. the key which is key k star, plus this expected value, and we want this to be 0. It's worth noting that k and n are fixed by the block cipher's properties, hence all we can do is vary R. So these are good values for R equals 2 for AES 128 and 192, and R equals 3 for AES 256. Now let's imagine a basic brute force attack. We can imagine first a naive brute force attack, where we simply enumerate our keys and test them. Does chi evaluate to 1? If it does, we're happy, return the key. If not, try the next one. We obviously need an exponential number of queries, i.e. 2 to the k queries, and each query costs an evaluation of chi. Alternatively, you can imagine a slightly more smarter approach where we evaluate a full function chi if and only if it passes one of these individual tests. And if we look at the cost of this, well, we still need to make the same number of queries, as the key could be any one of the number of candidate keys, but we've shifted the cost from the expensive test to a relatively cheaper test. And this is going to be the strategy we use. Now, as we're considering the quantum resources required to mount an attack, we should consider the basics of quantum computation. So an arbitrary k-qubit quantum state can be written as the sum of k-qubit computational basis states. Now these can be thought of, for our purposes, as bit strings of length k. Each computational basis state has its corresponding complex amplitude, and if we measure this quantum state, it will collapse to a bit string of length k with probability of the magnitude of that particular amplitude squared. Now in particular, each quantum state can be thought of as a vector, a complex vector of dimension 2 to the k. Hence quantum algorithms can be thought of as unitary matrices of dimension 2 to the k by 2 to the k. And these quantum algorithms can be built out of smaller gates or smaller unitaries acting on 1 or 2 qubits. Now ancilla qubits can decrease the cost of implementing these unitaries. So V may be the unitary we want to implement, but we may actually implement it as U, which acts on a larger state. As the ancilla qubits start in the same state and end in the same state, we can essentially factor them out, and for all intents and purposes, U and V then implement the same operation, but U may be vastly cheaper to implement. So the metrics we're going to consider are the number of quantum gates, or number of primitive quantum operations we perform, the quantum circuit depth, or time, and the number of qubits. And in particular, we're going to be considering two metrics. One, the G cost. So if we consider this circuit down here, each wire represents a qubit. We have 8 time steps, and we have 11 gates in total. Therefore, this particular circuit has a G cost of 11, because we have 11 gates. The other metrics we can consider is the depth-width cost, which is simply the product of the depth of the computation times the number of qubits we require. And this is designed as a rough estimate of the amount of error correction we may require. So we can consider the qubits as being idle, but they'll need some effort to maintain. Now, one particular circuit we'll be interested in is the quantum oracle. So for any classical circuit, say chi here, which is our search function, we can define a quantum oracle, which simply takes the computational basis state and flips the amplitude if chi of x is equal to 1. But we'll actually want to implement it more like this. Now for our purposes, the number of bits to represent k will be relatively small, but the number w will be large, and we'll be aiming to reduce this. Now the main tool we'll be using is quantum amplitude amplification, which can be thought of as a quantum algorithm which exploits the relationship between an arbitrary quantum algorithm, which has an adjoint, and a quantum oracle, based on the function chi we discussed earlier. Now, if we prepare the all-zero state, and apply the quantum algorithm A to it, measure it, and it gives us a bit string that satisfies chi of x equals 1 with probability A, then we can apply t iterations of a certain loop and boost the probability to this thing. So explicitly, we take the zero state, we apply the quantum algorithm A, and then we run this loop t times. And this loop consists of applying the quantum oracle, applying the adjoint of A, reflecting around the zero state, and then applying the quantum algorithm A again. To see the utility of quantum amplitude amplification, it can be compared with a scenario where we can only prepare this state here and measure it. Now if we can only do that, then we require resources equivalent to 1 over A, applications of A and chi. But if we use quantum amplitude amplification and choose the special value of t here, then in order to measure an element that satisfies chi of x equals 1, we only require resources equivalent to the square root of 1 over A applications of A, its adjoint, and the quantum oracle based on chi. Now, Grover's algorithm is a simple quantum search algorithm where we choose the initial algorithm A to be the Hadamard transformation on k qubits, and this has the nice property that it prepares the uniform superposition, i.e., if we know that there's only one element we're looking for, then we know this probability A, i.e., it's 1 over 2 to the k. Now, since the Hadamard transformation has a negligible cost compared to any non-negligible quantum oracle, Grover's cost can be approximated by this figure here. So if we go back to our analogy with classical brute force attacks, then Grover's algorithm has a cost that's equivalent to naive brute force search, i.e. we're gaining a square root in the number of queries, but we have to make quantum queries as opposed to classical queries. And what we're going to be looking at is a technique called the search of two oracles technique, which can be thought as the quantum version of this brute force search with filtering technique. Now, in the search with two oracles scenario, we have two circuits, chi and gamma, and we're looking for a unique element, x star, such that chi applied to x star is equal to 1. i.e., in our scenario, this is going to be the key we're looking for. And we also have a function gamma that identifies x star, but it also identifies a number of false positives, i.e., it can identify some weak property. So we have this relationship here, and this can be thought of as Grover's algorithm, and we have this additional bit of information in the search with two oracles scenario. Now, the authors of the search with two oracles paper define 3 algorithms that can solve this problem. Firstly, if gamma is actually more expensive than chi, then we simply use Grover's algorithm with the quantum oracle based upon chi. The other case considers where gamma is cheaper to operate and implement than chi. In this case, there are 2 algorithms we can use. One, a fully nested version of quantum search, and another algorithm which interpolates between Grover's algorithm and the fully nested version of quantum search. So we'll first explain the fully nested version and explain why we don't use it. So in analogy to Grover's algorithm, we can define an algorithm using the Hadamard transform, the oracle based upon gamma, and this magic value of t that terminates with the probability of 1 of measuring an element x that satisfies gamma x equals 1. Now, since we know the size of the set that gamma defines is s, and we know that's one element we're looking for, this has a probability of 1 over s of satisfying gamma x equals 1. Hence, we can simply define a recursive use of amplitude amplification, where we define amplitude amplification algorithm C using the quantum algorithm B, which we define here, and the expensive quantum algorithm based upon chi. And it turns out the cost turns into this formula here. So we can see the number of total calls to chi has been reduced, but we still have this query complexity of the square root of 2 to the k calls to the cheaper oracle, the gamma. But unfortunately, we have this constant increase here, and that's what the interpolation algorithm really does. It reduces this constant down from about 1.23 to 0.79, and we're going to just briefly go over that. So if we use the small angle approximation to get this success probability for applying amplitude amplification and use a far smaller number of clocks so this equation holds, then we can run through the entire process again, where instead of fully amplifying the initial state to get a success probability of 1 here, we end up with this figure here. So we have a probability of success of this, of measuring an element that satisfies gamma x equals 1, hence, again, we divide through by s and get our success probability relative to chi. Again, we then define our new algorithm C using calls to B and the quantum oracle based on chi. And this essentially gives the asymptotic behavior of the algorithm. We have that if t equals 0, we have Grover's algorithm, because we have the cost of Grover's algorithm here, and no calls to gamma. And if we have the magic value of t, then we have the fully nested version. But in between is where we're interested. And as we can see, as we slowly increase t from 0, we decrease the cost contribution of the expensive oracle, whereas the cost contribution of the cheaper oracle remains roughly static. And this diagram really shows the behavior. So this green line here is the current best attack on AES 128. the x-axis represents the number of inner clocks t that we're making for our algorithm B, and the blue line represents the cost of our attack on AES as a parameter of t. So as we can see, we've designed an expensive oracle and we're using Grover with it, so initially it's far more expensive than the best attack, but then as we increase t, the total cost of the algorithm decreases, but then we get this constant blowing up again if we attempt to use a fully nested version of quantum search. So how do we actually construct these quantum oracles based upon chi and gamma? Well, we can implement these quantum evaluations, which accept the computational basis state based upon the bit string x, a number of ancilla qubits, and 1 qubit for the output for chi or gamma. And the output, in the last qubit, the answer we're looking for, plus enough information to make the entire process reversible. And we can combine this with the Z gate, which acts upon 1 qubit, and if it's 0, it leaves it alone, and if it's 1, it adds a phase of -1. So here we have the basic design methodology. We start with the computational base state with x and the number of 0 qubits. We apply the quantum evaluation, which outputs the answer chi of x. We apply the Z gate on the last qubit, which gives us our conditional phase inversion, and then we uncompute g of x and chi of x using the adjoint of the quantum evaluation. So in general, if we have a classical circuit, we can construct a corresponding quantum circuit, and we can use these primitives here. For further information, I highly recommend looking at the Microsoft paper on the implementation of AES, which provides Q#, code which we'll later use. So we'll construct our quantum oracle for chi and gamma out of individual quantum evaluations for AES. i.e., they'll accept a key, a plaintext, have a number of ancilla qubits, and they'll output some information we're not interested in, i.e. g of x, and a ciphertext we're interested in here, and this can then be used for comparison. So we'll follow the design of the Microsoft paper in our implementations, which accepts the key, the plaintext, has enough space to write out the individual rounds, and does so. And then this final round here will be actually the encryption of the plaintext under the key here. Now generally, cryptanalysis of AES is performed in conjunction with a parallel oracle. So we can see here, each wire represents a number of qubits. We simply copy out the key to these qubits here, perform all the tests in parallel, perform the conditional phase inversion, and then uncompute the ancilla qubits, and then uncopy the keys. But we can equally do the entire process with a serial oracle, which, as we can see just by counting the wires, requires far fewer qubits, but has a much larger depth and uses far more of these individual components. So if we look at the circuit statistics for AES 256 and the ratios involved, then we can see that the parallel oracle uses a lot more qubits, but has a far smaller depth. So for the expensive quantum oracle based upon chi, we'll want to use the serial oracle, as this minimizes the number of qubits, but is expensive in both terms of gates and depth. And by using the search of two oracles methodology, what we'll actually end up with is an algorithm that uses the equivalent of the qubits of using the serial oracle, the depth of using the parallel oracle, and far fewer gates than either. So when it comes to designing the cheap oracle, we need to do a bit of hacking. It turns out the error in the probability of success for the Stowe algorithm is reliant upon the estimation of S, as this affects the ratios 1 over S and S over 2 to the k, i.e. the ratios of the number of targets for chi, 1, S, the number of intermediate targets in the search space defined by gamma, and 2 to the k, the number of targets in the entire search space. So instead of using just a function gamma, we define gamma hat, where gamma is do the encryption to plaintext and ciphertext match on 4 specific bytes, and check bits 20 is does k start with 20 leaving zeros. So why do we do this? Well, the number of solutions to check bits 20 is obviously 2 to the k minus 20, and if we have some variance in the size of S, which is defined just by gamma, then essentially this swamps this variance. So we get that we can reliably predict S hat. Now when it comes to AES, AES consists of a various number of rounds, depending on which flavor you're using, which consists of starting with state, so these are these rectangles here, going through the S-box layer, a fixed permutation layer, mixed columns layer, which is linear and affine transformation, and then XORing the key stage with it. And this is identical in all AES variants, apart from the first round and the last round are subtly different. The last round, for instance, excludes the mixed columns operation. So let's see what gains we can make if we hack into this circuit for AES. This represents the last 3 rounds of any AES computation. So if we only want to test these 4 bytes, then we only have to compute these 4 bytes. So if we trace back, we see that we can remove some stages of the key expansion, add addition, the S boxes, remove 3 mixed columns operation, continue on, we can remove further S boxes, further XORs until we reach the mixed column stage. Now this is problematic as it has 4 input bytes and 1 output byte, but we can still further hack this, and in fact we get a reduction in the depth of this particular circuit. So we get a small saving here, but no change in depth. But we have an option here because we're now using fewer qubits. So these qubits can then be repurposed to either reduce the depth of this stage, or we can further squash down the size of the quantum evaluations in the expensive circuit and make it far more expensive while using fewer qubits. We coded up these oracles in the Microsoft Quantum Programming Language Q# and based them upon the quantum circuit evaluators for AES that Microsoft themselves produced. So we could use the STO methodology with simply these oracles, naively, but our modified oracles are here. So this top line represents the possibilities for the cheap oracle, and this bottom line represents the possibilities for the expensive oracle. As we can see, we have a pure win in all metrics for the cheap oracle, apart from perhaps t-depth, and for the expensive oracle we've reduced the number of qubits, but we've increased the depth and all the other costs. But when it comes to actually using the STO methodology, we get these circuit metrics. So if we execute a quantum algorithm using Grover, we'd have these costs, where r equals 2, r equals 3, and our methodology, we get these costs here. So we can see the circuit depth is relatively left unchanged of the entire attack, but we use far fewer qubits, and we have a win in both the g-cost and the depth-width cost. A natural question to ask is what happens when we have a limit on the maximum allowable quantum circuit depth, i.e. a time limit on the amount of time we can run the quantum algorithm for. Well, in this case, one solution is inner parallelism, which is to be studied by the Microsoft paper on implementing AES. In this case, you take 2 to the p different quantum computers and you just simply fix the first p bits of the key. This leads to an expected number of solutions to chi of this figure here. Now as p has been increased, we have to worry less about r. So in fact, as p increases, we can reduce r. So in Grover's algorithm, the cost becomes r to r hat. And we get this blow up, which due to the poor parallelism of Grover's algorithm. Whereas the effect on the search for 2 oracles algorithm is we don't care about r anyway. So we get less of a gain. And in fact, if r hat is equal to 1, then essentially the cost will be the same. So this is what we see. In the max depth equals 2 to the 40 or 2 to the 64 scenarios, we're going to use one plain text ciphertext pair anyway. So we see negligible gain. And this negligible gain is only from the fact we're using a reduced cost, cheap quantum oracle. But in the max depth 2 to 96 scenario, we get that gain because we naively, using Grover's algorithm, have to use r equals 2 plain text ciphertext pairs anyway. So in summary, we have minor gains, but they're applicable to cryptanalysis of all block ciphers. AES is 1 bit less secure in a specific max depth scenario, and we require fewer qubits to perform cryptanalysis, which is purely a good thing. Thank you very much for your time. We have some acknowledgements and references here, and I hope you enjoyed the talk.